the fidelity looks a bit lower. I'm sort of accustomed to getting to the higher fidelity that you've given us in the past two use cases. And I wonder, is this, I know that there are memories that are located within the repeaters, and that drives the specification of decoherence time for the repeaters as a whole. And I'm wondering here if maybe we could upgrade the repeater memories, the repeaters, to be not just good, but maybe a better repeater with better decoherence times, or maybe even potentially gold standard decoherence times. Maybe that's another factor that we could pull in here to improve the fidelity and turn this into a network that could genuinely be multi-purpose.
Yes, Mike, let's go ahead and do that. Let's improve our coherence times for each of the memories. And all right, this time we're using 1 millisecond coherence time. So let's improve that to 10 milliseconds this time. So let's change this for our 8 quantum memories. Okay, just one more. And okay, this is looking good. 0.01 for each of our memories. And then again, let's change our log file name and run this simulation. Okay, I think it ended, faster than the other ones. Maybe we got an even better, swapping behavior this time. But let's see. Okay, network file. Here is our third log file, and let's see what we got this time. So scroll down. Yep, we definitely had more success in the swappings this time. But yeah, what we are looking at this for this simulation is actually the fidelity, right? You can see how it definitely improved after with better coherence times.
Now, this is a wide area network that I could stand behind. This is something that's multi-purpose. I think it'll support a wide range of use cases with this fidelity, the swap success. I could see running key exchanges over this. I could see running distributed quantum sensing eventually. Again, I could even see eventually it possibly doing blind quantum computing, connectivity, maybe even interconnecting quantum computers. Now, it's interesting because the change in the repeaters, we know that there's a number of factors there that influence the parameters and the profiles and the characteristics of repeaters and memories as they become, as we approach a production, quality here and reliability. But even just the types of memories, there's ion trap and supercomputer type memories. Those can actually influence the characteristics also. Now, Michelle, one thing I'll ask you here is that this really looks quite simplified, even though I know it's incredibly complex. And a couple of the things that go into this are, one aspect here is the fact that the communications and the protocols that are used to create all of this communication back to other nodes to let them know that a swap was successful or entanglement didn't happen, and letting everybody know to reset and start over. All those things are, I think, very unique quantum networking protocols and capabilities and communications. Now, are those things that Aliro does? I mean, does Aliro actually implement those kind of unique protocols and to perform this a system like this and support a system like this?
Yes, you're right, Mike. This is, when you are looking at, this kind of complex simulation, we're gonna be, we're looking at trying to tell the other nodes what to do depending on what's occurring in the rest of the simulation or in the rest of, in the other nodes of our network. So yeah, here at Aliro, we have developed a protocol to actually communicate, these nodes, and to for each of those nodes to understand what to do. So yeah, that's the communication between nodes is something that we're developing here at Aliro.
That's great. I know there's a lot of intellectual property that goes into this, and there's 4 years of development and almost a dozen patents and 10 times as many claims that are involved in all this technology. So it's